Hello everyone, welcome back. My name is Mr. Kowalt, and in this video we're going to find the pH of a solution of a complex ion, and then we're going to also look at whether or not a solution involving iron 2 ion is going to be more or less higher or lower pH than a solution of the same concentration of iron 3 ion. So let's get into this. Okay, so in this problem, we're told that the equilibrium constant Ka for the reaction below is 6.0 times 10 to the negative 3, and that reaction is the complex ion involving iron and water, so Fe H2O 6,3 plus aqueous plus water is going to give us the Fe H2O5 with an OH ion or OH hydroxide ion with a 2 plus, and then that gives us the H3O plus hydronium ion. And so what you have here is you have the complex ion involving iron, which is going to be iron 3, and 6 waters are complexed or bind as ligands to your iron here, and it has an overall charge of 3 plus. And so what happens is these water molecules become acidic, right? So the hydrogens here can come off, and that's what you see here. So one of the hydrogens of one of the waters here comes off, is donated to the water molecule here, leaving 5 water molecules as ligands, and the water molecule that donated its hydrogen is then a hydroxide ion or ligand, in this case bonded to the iron here, giving us the hydronium ion, and that's going to be in equilibrium. And so we're asked first, calculate the pH of a 0.10 molar solution of this solution of the complex ion. And then for part B, we're asked, will a 1.0 solution of iron 2 nitrate be higher or lower in pH, or have a higher or lower pH than a 1.0 molar solution of the iron 3 nitrate? So we'll talk about that after we figure out what the pH of the solution is. Okay, so the first thing we need to do is do an ice table involving this reaction here. So if I do my ice table here, if I rewrite the reaction Fe H2O6 3 plus H2O in equilibrium with Fe H2O5. Oops, that's not a H2O 5 with OH, and that's a 2 plus the hydronium ion. And then I do my ice table like so. So the initial concentration is 0.10 molar, so we'll put that here, 0.10. We're going to ignore water. And so to start with, these are going to be 0 in concentration. So therefore, it's going to shift this way to make product. And so we're going to lose, since this is a 1 to 1 to 1 ratio, we're going to lose an X amount here. And we're going to gain an X amount here and here. And then we add these together, we get 0.10 minus X. And this is going to be X and X. Okay, so now that I have my ice table set up, I have my equilibrium concentrations in terms of X. So now I can put that into my equilibrium constant expression, which for this is going to be Ka is equal to, we said 6.0 times 10 to the negative 3, so 6.0 times 10 to the negative 3, which is then going to be equal to the concentration of products raised to the power of their coefficients. They're both 1, so this will be the concentration of Fe H2O5 OH 2 plus, times the concentration of the hydronium ion, HO3 plus, all over the concentration of FeH2O6, 3 plus. So concentration of FeH2O6, 3 plus. And again, we're not including water in our expression because you don't include solids or liquids. So since water is a liquid, it's not going to end up in our expression. And so now we can plug in our equilibrium expressions in terms of X. So both of these concentrations are X. So X times X is X squared. And then this is going to be replaced with this concentration, 0.10 minus X. So 0.10 minus X. So now we have this is equal to this, and we can solve for X. Now, we're going to do the X is small approximation or assumption and see if that is valid. And so here, what you can see is if you look at the initial concentration here, 0.10 or 1 times 10 to the negative 1, and here the K value is 6.0 times 10 to the negative 3. Negative 3 times 10 to the negative 3 and 10 to the negative 1 is just a difference of maybe 100, which seems that it's probably not going to pass the test for the X is small. So it's probably not going to be valid, but let's check that out and make sure. So then what we're going to do is we're going to take the, I'll use this space here. So we're going to take we're going to do the X is small, so we'll say this is negligible. So we'll say X is so small that subtracting it from the initial concentration is really not going to matter. So we're going to say that the equilibrium concentration here is going to be the same as the initial concentration that we started with. Okay, so that means that we can now multiply both sides by 0.10 over here. We're going to multiply this by 0.10 over here. And then we get, this answer will be 6.0 times 10 to the negative 4. And that's going to be equal to X squared. And if we take the square root of both sides, we get, what do we get? 2.449. So X is going to be equal to 2.449 times 10 to the negative, I want to say negative 2. Yes, negative 2. So that's our X value. And, oops, excuse me. So this is our X value. So now we can figure out whether or not this is valid. We're going to do the 5% rule. So we're going to take the initial concentration that we have. So the initial concentration is 0.10, and we're going to take the X value, the change here. So 2.449 times 10 to the negative 2. We're then going to divide that by 0.10, the initial concentration, and we're going to see what the percent of this is. So we're going to multiply by 100, and then when we do that, we get 24.5%. So this is going to be equal to 24.5%. So that tells us that 24.5% of this ionized, which means that X is pretty large. So X is definitely not going to pass the test because the 5% rule says in order for this assumption that X is negligible, the percent here has to be less than 5%, but obviously it's not less than 5%. So we can't use the x is small or negligible assumption. So here we're going to have to go through the method of successive approximations. And basically what that is that we are going to take our expression here, the K expression, so Ka is equal to 6.0 times 10 to the negative 3, and that's equal, as I said, is x squared over 0.10 minus x. And all we're going to do is we're going to take our x value, we're going to say this is x1, and we're going to perform an iterative process by which I take my x value that I found using the x is negligible assumption, and I'm going to just plug it back in here and solve for x again. So basically I'm going to take it, put it in there, I'm going to subtract from the initial concentration, and then as you saw I'm going to multiply by the Ka value and then take the square root and then repeat that process until I get the same number in a row, right? So I'm going to take this number that I get for my x, plug it in, subtract, multiply by the Ka, take the square root, and then take that number, do it again, put it in for x, subtract, multiply by Ka, take the square root, and I'm going to do that until the x value that I get is the same twice in a row. So here we go. So I'm going to plug this value in, right? So that's going to be equal to x squared, and this is going to be 0.10 minus, and then this here is going to be 2.449 times 10 to the negative 2. And then when I subtract those, I get 7.551, so it's going to be x squared over 7.551 times 10 to the negative 2. And then I'm going to multiply both sides by the bottom here. So I'm going to multiply this by 7.551 times 10 to the negative 2. Multiply this by, so let's get rid of this. So I'm going to multiply this by 7.551 times 10 to the negative 2. And when I do that, I get 4.5306. So now I get, let's see, 4.5306 times 10 to the negative 4. That's going to be equal to x squared. Take the square root of both sides. And now x is equal to, oh, this is going to be the second iteration, so x2. So we have x1, x2, and then what do I get for x2? 2.128. So 2.128 times 10 to the negative 2. And so you'll see here that this x1 that I got, the first x value I got, and the second x value I got are not the same. So I got to do it again until I get a repeated value, a successive value that's the same twice in a row. So I keep doing this, same thing. I'm going to plug this x2 into x here, subtract it from 0.10, multiply by the Ka value, and then take the square root. And I'm going to do that each time. So I'm just going to give you the values that I calculated. So here I got x2 there. I'm going to erase this to give myself some space. When I do this again, I get my third iteration of x is going to be 2.173. So 2.173 times 10 to the negative 2. And you'll see here the second and third iteration are not quite the same, so I got to do it again. And when I do it again, I get the fourth iteration of x is going to be 2.167. 2.167 times 10 to the negative 2. So again, the third and fourth iteration, very close, but not close enough. So again, I gotta do it one more time. And when I do that, I get it repeated. So the fifth iteration of x ends up being 2.167 times 10 to the negative 2. And so you can see that I have the same number twice in a row. So here, my final x value is going to be 2.167 times 10 to the negative 2. So that is the value of x that I am looking for. And so now I can do the pH. So since x is the same as the H2O plus, the hydronium ion concentration, remember that pH is equal to the negative log of the hydronium ion concentration, H3O plus, or H plus for short. So this is going to be equal to the negative log of my X5 here, 2.167. 2.167 times 10 to the negative 2. And so I calculate that, and I get a pH of 1.66. So 1.66 is the pH that I get. Okay, so that's the answer to A. What about the answer to B? Okay, so let us erase this. Okay, so here we're given a 1.0 molar solution of iron 2 nitrate and a solution, 1.0 molar solution of iron 3 nitrate. And you'll notice that here we're looking at iron forming a complex with water, iron ions that form a complex with water. And when it forms a complex with water, it becomes an acidic substance such that the water molecules, the hydrogens that normally wouldn't, they do come off here, but then this becomes more acidic, so it's actually allowing the hydrogens of the water to come off more easily, and so you get this process here where H comes off and is donated to water. And the question is like, would the iron here that's forming the complex, if it has a positive 2 charge or a positive 3 charge, would the solution that forms this complex, would it be more or less acidic depending on whether you have an iron 2 ion or iron 3 ion? So we'll have to look at both of these. First, nitrate ion, if we look at the anion here, nitrate, which is NO3 minus, this is the counter ion, or the, how should I say, the conjugate base, or the negative ion of a strong acid, right? So HNO3, nitric acid, is a strong acid, which means that this is going to completely ionize in water. So that means that this ion here, with the conjugate base, is going to be so weak that it's not going to remake HNO3 here. So it's very heavily slanted, or how should I say? It's very much in favor of forming the products of hydronium ion and your nitrate ion. So it'd be very much heavily that way, right? So that indicates that this is really not going to form it's not going to reform this by reacting with water. So we can ignore this as a neutral ion as far as pH goes. Okay, so then what we need to focus on is the iron 3 plus ion versus the iron 2 plus ion. So what's causing the acidity in this complex here? So the acidity is being created in this complex by the fact that the iron here is a relatively small atom or ion in this case. So here, if we have the iron 3 plus ion, that's a very large charge for an ion. It's very small. So that very small ion with a large charge is going to have a very strong attractive force pulling the electron density away from the waters that are bonded to the central atom ion here, the Fe3 plus. And so that's going to take, excuse me, that taking away of the density of the electron density from the water molecules is then going to make the bonds in the water molecules between the hydrogen and oxygen weaker, therefore allowing them to be given off or transferred to a water molecule more easily, right? So that causes the acidic nature of the complex. Now, if we compare that with iron 2 ion, well, the charge on the iron 2 ion is not as great. So therefore, this charge here is not going to have as strong of a pull on the electron density from the water molecules, therefore not weakening the bond between the oxygen and the hydrogen as much as the iron 3 plus ion would. And so therefore the hydrogens on the water molecules that are bonded or ligated that act as ligands in the complex ion here are not going to be given off as much. The bonds are going to be a bit stronger, and so therefore the hydrogens are not going to be donated as easily, and therefore it's not going to be as acidic. So since acidity is measured by pH in a way that the more acidic your substance is, the lower the pH. So therefore, if iron 2 plus is going to not pull the electron density as much, therefore not weakening the bonds between the hydrogen and the oxygen in the water, therefore it's going to be less acidic and higher pH. So we would say that this is going to be less acidic. This is going to be more acidic. Therefore, since this is less acidic, this is going to have a higher pH. And since this is more acidic, it's going to have a lower pH. And that's it for this video, this problem. I hope this was helpful. I hope I was able to help you understand this better. If so, if you like this video, if you enjoyed and learned something from this video, then please by all means like the video, share the video, hit that like button right down there. Also, subscribe to my channel, hit that notification bell right up there. As soon as you do that, hit all so you'll be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.